Well, thank you very much for the kind introduction and welcome to my presentation entitled Evacuation Simulation of a Flying V Aircraft using Cellular Automata. I would like to start off this presentation by showing two videos. The first one is about how the Flying V project was started in the years 2013, 2014, and 2015. Now, the second video is a very recent one, a historic event which took place last year. It is the first flight of this scaled flight demonstrator, which was created by researchers at TU Delft, who are currently continuing this project together with several partners.
5, 7, 9, 11, 13, 15, 20, 22. In the air. I continue. Yes, 24, 25. 28. 33. Batteries are at 80. You're currently at 6 degrees. It's a bit heavy. Moving back, clear. Speed is good. Speed is high and good. It's been 2 years of intense, stressful work to reach this moment, and then to have it confirmed that it flies. All of that hard work. It was worth putting in all of the hours, making sure everything's correct and built properly, built accurately, and it pays off. I think we're all happy that we succeeded and achieved the goal of flying the Flying V.
Now, what is the Flying V? The Flying V is a new concept for an efficient aircraft. Here's the first picture, and the concept was introduced in 2014. Basically have two passenger cabins which are arranged in the shape of a V. This concept was further developed over the past 5 years by researchers at TU Delft, a project led by Rolf Voss. Here's the concept as it looks today. Most interesting change here is that passengers are more to the front of the aircraft and cargo is more to the outside. First, let me show you a 3D render of that concept, which has been further developed. And of course, this is not only done by TU Delft. Several partners are involved. Indeed, also Technical University of Braunschweig is involved in that effort. But of course, main project partners are Airbus, TU Delft, and KLM. And tubulin is also active currently. So what we do to help with that are two projects: evacuation simulations and CFD simulations with the Lattice-Boltzmann method. Both of these projects are somewhat related to a course in numerical simulation, which is taught by Dr. Hess and myself at TU Berlin. Now, evacuation simulations. This talk is about this topic. This is what Julia Gebauer, who was also in the talk today, and I have done over the past months. Here you see a very rough discretization of the flying V cabin and of the reference aircraft. And now, what you do is you create a very rough model here using cellular automata, and you try to compare both aircraft with regard to emergency evacuation, because certification regulations state that passengers must evacuate the aircraft in 90 seconds when half of all doors are closed. So this is what we want to model with this simulation, and we do a preliminary simulation with a very rough model. As you can see here, we do not even meet the geometry 100%. There are slight differences. You can see that the length of the cabin does not fit very well. There are other problems, but it's a first preliminary model which gives us an idea of evacuation times. Now, what we use for that effort is the so-called floor field model. It was developed by Burstedt, Clark, Schatzschneider, and Zitas in the year of 2001. We basically use a gradient field, which tells people how to leave the aircraft. And then we layer other layers on top of this field. For instance, another one here in green, which adds some entirely random motion to the passengers. So one field tells them to go outside and leave the aircraft. The other field basically says just move randomly. And then we calibrate this level of random motion to meet some values for evacuation of existing aircraft configurations. We can add other layers, for instance, a small correction layer, which is shown here in red, so that people do not get stuck in dead ends, for example. Now, with this very rough model, of course, we have some problems. For instance, where both legs of the flying V meet, where both lattices are aligned with the legs of the V, people need to transition from one leg to the other, which is a sort of a problem of this preliminary model. But we solve this in this model using transition conditions. Now, here's a diagram which shows you how we calibrate our model. I told you that we add a level of random motion to the passengers. And here you see evacuation times on the y-axis and this calibration parameter R on the x-axis. So this is basically no random motion here to the left for very small parameters of R and very high random motion of passengers for very high parameters of R. And as this parameter R increases for the random motion, then of course the evacuation time increases. Now this red line shows known evacuation time data from known aircraft configurations. So we have our reference aircraft, the A350, and for that aircraft, of course, you know how long passengers take to leave the aircraft. So we use this time, here 60 seconds, to calibrate our model. So our parameter R is set to this value here. Now, of course, you see flying V evacuation times are a little bit higher. We'll get to that in a second here. How does that look? How does an evacuation simulation look here? You have always a comparison of reference aircraft and flying V. Both lattices are shown here. Here again, one lattice, and here two lattices with transition conditions in the middle section. And let me show you how this simulation runs. All doors on the right side of the aircraft are closed. So this is one of the cases which has to be investigated. And you see that, of course, the A350 performs a little bit better, although we do not exceed the 90-second mark for the flying V. Here we are with the calibrated model at 82 seconds. This rule of closing only the right side or left side of the aircraft comes from traditionally from fear of a fire of one of the engines. And if one of the engines is on fire, of course, you think that the doors to the right side of the aircraft might not be able to be used for the evacuation. Of course, for the flying V aircraft, this may not be applicable here because engines are to the back of the aircraft. So keep that in mind while we show these results here. Now, we did not only test configurations where only the doors on the right side of the aircraft were closed, because certification regulations state that half of the doors must be closed. They don't specify which doors. So we tested some other cases here, and these are the results of the study which was done by Julia. And she basically found that for when all doors are open, here this is case 1, evacuation times are comparable at around 35 seconds. Then this is the case, the second case, which I believe is the most critical for the flying V, which I showed you here. So the doors on the right side are closed and doors on the left side are open. But here's an interesting thing. What you see is, look at cases 5 and 6. This basically shows you that when people have to move more to the front or more to the back of the aircraft, they move much faster through the flying V because you have more aisles. This has been also found in simulations, recent ones, where the flying V where the boarding of the flying V was simulated. So what you see basically here with the preliminary model is that when people transition front to back, it's a little bit faster, and when they move from one side to the other, it's a little bit slower. All right, so we did not stay there. This is a very recent model. This may be also interesting for guys who use cellular automata. What we did here is we increased the resolution of the lattice. So this is a very fine lattice here. So, and one dot, one of those blue dots, occupies way more than one cell. So there's a real radius of cells, which is occupied by one passenger. And through this, we get a more fluid motion of passengers. And we are able to include things like walls and obstacles. And currently, we are developing this model a little bit further to do more research of the evacuation process and to develop guidelines how to improve the cabin of the flying V to increase evacuation times. Let me show you this video. There's a way more fluid motion here, but you see the same trends when all doors on the right side are closed. So there's a little jam formation here. But you see also what still needs to be developed in this video. So for instance, this guy, he waits here, although everything here is free. So they don't look for another way yet. So this is something we'll work on as well. Yeah, let's wait here. We did not show any times here yet because this model is also not calibrated, or any comparison to the reference aircraft has also not been performed yet. So this is part of future research. So let me conclude here. We performed a preliminary analysis of the evacuation of the Flying V and the A350 reference aircraft. A simple simulation tool was presented, and the passenger decides where to go by a probability, by layering different fields. And we used a single parameter to characterize the random motion of passengers during the evacuation process, and use that to calibrate the model to match evacuation times of existing airplane configurations. With this calibrated tool, we performed multiple simulations for the Flying V and the Airbus A350. And the Flying V cabin has advantages over the longer conventional reference cabin for cases when passengers need to evacuate towards the front or the back. And some disadvantages occur when passengers need to evacuate towards one side of the aircraft. You should exert great caution with the results of this study, especially with quantitative values. A more detailed simulation model to further investigate the topic and substantiate the results given in this preliminary study is currently under development. Who are these people? There's Julia Gebauer, who did this work, Raphael Hellmann, who improved the model which I showed you in these last slides. And from this point on, George Franosch and Josephine Wilhelm will continue this study. With that, I'd like to thank you very much for your attention.